Hello, everyone. Today we are going to learn the basic arithmetic operations of derivative. Let's review how to find the derivative of y equals fx. We know the definition of derivative. We can use the definition of derivative to find the derivative of function, but this involves the calculation of the limit. It is not any function. We can get its derivative by definition. For some special functions, such as basic elementary functions, we can directly obtain their derivatives through the derivation formula. Recall that we learned about the derivatives of some basic elementary functions. In the previous lesson, we got 6 groups of derivative formulas. First, the derivative of a constant function is 0. The second one is that the derivative of the power function to the power of x alpha is alpha times alpha minus 1 power of x. The third and fourth are trigonometric functions. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. The fifth one is the derivative of the exponential function a's power x is e's power x multiplied by ln a. Specifically, the derivative of e to the power of x is still e to the power of x. The sixth one is the logarithmic function, where the derivative with a as the base and x logarithm is 1 of x multiplied by ln a. Specifically, the derivative of ln x is 1 of x. We know that many functions can be obtained through the addition, subtraction, multiplication, and division operations of basic elementary functions. Finding the derivatives of these functions by definition can encounter many difficulties. And now, we have obtained the derivatives of basic elementary functions. So we look forward to using the basic elementary function derivative formula that has already been obtained to solve it. In this lesson, we will study the basic arithmetic operations rule for derivatives, which involves finding the derivatives of the sum, difference, product, and quotient of basic elementary functions. Let's take a look at how to calculate the derivative of this function together. hx is equal to x squared plus x. The function hx can be seen as the sum of two functions. One is fx equal to x squared, and the other is gx equal to x. So, what is the relationship between the derivative of function hx and the derivatives of these two functions? To study this problem, the first step is to calculate the derivative of hx. So, how to find the derivative of hx? At present, we can only calculate its derivative through definition. Let's take a look at the definition of our applied derivatives together. How to find the derivative of hx? Firstly, we calculate delta y to delta x. Delta y is equal to the square of x plus delta x plus the sum of x plus delta x minus the square of x plus x. Here, the square of x plus delta x can be expanded to the x square, and the x square after it can be eliminated, and the x here and the x behind can also be eliminated. The numerator is delta x squared plus 2 times x multiplied by delta x plus delta x, and the numerator and denominator are approximately divided by delta x to obtain the result of delta x plus 2x plus 1. When delta x approaches 0, taking the limit yields the derivative of hx as 2x plus 1. So we obtain the derivative of hx. So let's observe fx, gx, and hx, and the derivatives of these three functions. What have you found? We will notice that hx is sum of fx and gx, and the derivative of hx is also the sum of the derivatives of fx and gx. That is to say, hx is written as the sum of two basic elementary functions, and in fact, the derivative happens to be the sum of the derivatives of these two basic elementary functions. You can choose multiple sets of functions and try them out. Is this relationship established? We speculate based on this that the derivative formula of functions and is equal to the sum of the derivatives of two functions. Similarly, it can be inferred that the derivative of the difference between two functions is equal to the difference between the derivatives of two functions. In this way, we obtain the derivative formula for the sum or difference of two functions. Generally, for the derivatives of two functions fx, gx, sum or difference, we have the following rule. The derivative of the sum or difference of two functions is equal to the sum or difference of the derivatives of two functions. Next, we will use this prediction rule to calculate the derivatives of some functions. Let's take a look at example 1 together. Find the derivative of the following function. The first question is that fx is equal to the cube of x minus x plus 3. The second question is gx equals 2 to the power of x plus cosine x. The third question is that hx is equal to e to the power of x plus the root x. Let's solve the first question first. fx can be seen as composed of the sum or difference of three functions. One is x to the power of 3, one is x, and one is 3. They are all functions of fundamental numbers. We can directly write the derivatives of these three functions based on the differentiation formula to obtain the fx derivative. According to the basic derivative formula we learned earlier, the derivative of x to the third power is 3 times x squared. The derivative of x is 1, and 3 is a constant derivative of 0. So the derivative of fx is 3 times x squared minus 1. Let's take a look at the second question again. Gx is composed of the sum of two fundamental elementary functions, y equals to 2 to the power of x and y equals to cosine x. So we can obtain the derivative of gx by taking the derivative of these two functions. This requires us to remember the derivatives of these two fundamental functions. Among them, the derivative of 2 to the power of x is the product of 2 to the power of x and ln 2. The derivative of cosine x is negative sine x. This gives the derivative of gx2 to the power of x multiplied by ln 2 minus sine x. Let's look at the third question again. The same method. Hx is composed of two basic elementary functions, y equals e to the power of x and y equals the root x. We will calculate the derivatives of these two functions separately. The derivative of e to the power x is the derivative of e to the power x. The root x can be written as 1/2 power of x, and its derivative can be obtained from the derivative formula of a power function. The result is the negative 1/2 power of x for one of two times, and we write it as double the root x by 1. So the derivative of hx is the power x of e plus 2 times the root x divided by 1. We have obtained the differentiation rule of functions and differences. Can we obtain a similar derivative rule for the product of functions? Using fx equal to x squared and gx equal to x as an example, calculate the derivative of the product of these two functions and the product of their derivatives to see if they are equal. This is not difficult to calculate. The product of two functions is the third power of x, and its derivative is 3 times x squared. The derivatives of the two functions are 2x and 1, respectively, and the product of their derivatives is 2x. Obviously, the product of the derivatives of two functions is not equal to the product of the derivatives of two functions. Let's double-check the derivative of fx equal to x squared and gx equal to x squared, and see if it is equal to the quotient of their derivatives. The quotient of two functions is x, so their derivative is 1, and the quotient of the derivatives of two functions is 2x divided by 1, which is 2x. The derivative of the quotient of two functions is also not equal to the quotient of the derivatives of two functions. In fact, we have the following rule for the derivative of the product or quotient of two functions. First, let's take a look at two functions. The derivative of the product is equal to the sum of the derivatives of these two functions multiplied by another function. The derivative structure of the two function quotients is relatively complex, with the denominator being the square of the original denominator function, the numerator being the product of the derivative of the original numerator function and the denominator function, and the difference between the derivative of the denominator function and the product of the numerator function. Specifically, for the derivative rule of function product, we can further derive that the derivative of the product of constant c and fx should be equal to the sum of the derivative of constant c and the product of fx and the derivative of constant c and fx. And if the derivative of constant c is 0, the result is the constant c multiplied by the fx derivative. That is to say, the derivative of the product of a constant and a function is equal to the product of the constant and the derivative of the function. This is equivalent to a special case derived from the product of two functions. Everyone can give it a try and see if they can get some more exceptions and inferences, such as the derivative formula for the reciprocal of a function. Next, we will apply the basic arithmetic operations rule of derivatives to find the derivatives of several functions. Let's take a look at example 2 together. The first question is that fx is equal to the cube of x multiplied by the cube of e. The second question is that gx is equal to 2 sin x divided by x squared. The third question is x squared plus 2x multiplied by the root x. Let's start with the first question. The desired function is that fx is equal to the cube of x multiplied by the cube of e. So the derivative can be obtained by using the derivative rule of function product. First, calculate the third derivative of x, then calculate the x derivative of e, and substitute it into the derivative rule for the product of functions. We can obtain the derivative of the function fx. And we know that the third power derivative of x is 3 times the x power square, and the x power derivative of e is e's x power. So if we organize it again, we can get the result as 3 times the x power plus x's third power multiplied by e's x power. Let's take a look at the second question again. The function gx can be seen as composed of the quotient of twice sine x and x squared. Then we will use the derivative algorithm of function quotient. The denominator is the square of x squared, which is the fourth power of x. The molecule is twice the derivative of sine x multiplied by x squared minus twice the derivative of sine x multiplied by x squared. Furthermore, the derivative of twice sine x can be regarded as the derivative of the product of a constant and fx. That is, twice the derivative of sine x itself, we can obtain the result as twice cosine x, and the square derivative of x is 2x. In this way, we obtain the derivative of gx as 2 times cosine x multiplied by x squared minus 2 times sine x multiplied by 2x divided by the fourth power of x. Subtract approximately 1x from the numerator and denominator, and then organize it appropriately. We can obtain the result is 2x times multiplied by cosine x minus 4 times sine x divided by the cube of x. The structure of the derivative formula here needs to be accurately memorized. Especially, this structure in the molecule should not be confused with the derivative formula of the product of functions. Let's take a look at the third question again. We can consider hx as the product of the function y equal to the square of x plus 2x and the function y equal to the root x. In this way, we can use the derivative rule of function product to calculate the hx derivative. It is equal to x squared plus 2x derivative multiplied by the root x plus x squared plus 2x multiplied by the root x derivative. Furthermore, by adding 2x to the square of x and applying the derivative operation rule, we can obtain its derivative as 2x plus 2. The derivative of the root x is twice the root x by 1. After organizing, we can write it as 2 times the root x 5 times the square x plus 6x. Of course, we can use a different conversion method. We multiply the root x into the equation and write it in the form of a power function, expressed as 5 second power of x plus twice x 3 second power. In this way, hx is written in the form of two functions and we can use the derivative formula of the sum of two functions to calculate their derivatives. The derivative of x's 5 second power is 5 second times x's 3 second power. The derivative of 2 times x to the power of 3 seconds is 2 times x to the power of 1/2. Further organization can be written as 5 second times x to the power of 3 seconds plus 3 times x to the power of 1/2. The derivative of 2 times x to the power of 3 seconds is 2 times x to the power of 1/2. Further organization can be written as 5 second times x to the power of 3 seconds plus 3 times x to the power of 1/2. Viewing functions from different perspectives can lead to different approaches to problem solving. In the process of calculating the derivative of a specific function, one should flexibly choose the solution approach based on the specific situation. Next, let's look at a practical problem. The drinking water in daily life is usually purified, and as the purity of the water increases, the required purification cost continues to increase. The function of the cost required to purify 1 ton of water to a purity of x% is fx equals to 50 to 84 divided by 100 minus x, where x ranges between 80 and 100. The problem is the instantaneous rate of change in the required purification cost when purifying to a purity of 90% and 98%. How can we determine the instantaneous rate of change in the required purification cost when the purity is 90% and 98%? We know that the definition of the derivative of a function clearly states that the derivative of a function at a certain independent variable value is the instantaneous rate of change at that value. So the instantaneous rate of change in the required evolutionary cost for purity levels of 90% and 98% is the derivative value of the corresponding function. Now that we have the derivative operation rule, there is no need to rely on definitions to find the derivative value of a function at a certain independent variable value. You can calculate the derivative of a function. Then, by substituting the corresponding independent variables into the analytical expression of the derivative function, the instantaneous rate of change when the values of the corresponding independent variables are taken can be calculated. Let's take a look at the answer together. Firstly, fx can be seen as composed of the quotient of a constant function and a linear function. So we will use the derivative rule of function quotient to find its derivative. The denominator is 100 minus the square of x. The difference between the derivative of the constant function 5284 multiplied by 100 minus x and the derivative of 5284 multiplied by 100 minus x, where the derivative of the constant function is 0 and the derivative of 100 minus x is -1. In this way, we obtain the derivative of fx is 5284 divided by square root of 100 minus x. Next, by substituting x equals to 90 and x equals to 98 into the analytical expression of the derivative function, we can obtain the derivative value of 52.84 when x equals to 90 and 1321 when x equals to 98. So we obtain the instantaneous change rate of purification cost at a purity of 90% and 98%. But what does this indicate? The value when x equals 98 is 25 times the derivative value when x equals 90. That is to say, when purifying to a purity of 980%, the instantaneous rate of change in purification cost is 25 times that of purifying to a purity of 90%. In other words, when purifying to a purity of 98%, the rate of change in purification costs is 25 times faster than when purifying to a purity of 90%. Finally, let's make a summary. What did we learn in this class? We studied the derivative operation rules of sum, difference, product, and quotient of functions. Through these algorithms, we can calculate the derivative of any function obtained through the basic arithmetic operations from a basic elementary function. Let's consolidate the basic arithmetic operations of derivatives again. First, let's take a look at the derivative operations of sum and difference functions. This structure is relatively easy to remember, where the derivative of the sum or difference of two functions is equal to the sum or difference of the derivatives of two functions. The prediction rule for the product quotient of a function is slightly more complex. Let's first take a look at the derivative of the product of two functions, which is equal to the sum of the product of the derivatives of two functions and another function. The derivative structure of two function quotients is more complex, with the denominator being the square of the original denominator function. The numerator is the difference between the product of the derivative of the original numerator function and the denominator function, and the product of the derivative of the denominator function and the numerator function. Special attention should be paid to distinguishing the derivative formula of function product quotient, because the derivative structure of the product of the numerator of the derivative of the quotient of the partition function and the function is somewhat similar, with the difference being that one is different from the other. Only by accurately memorizing the derivative formula of the basic arithmetic operations can we apply it to calculate the derivatives of more functions. That's all for today's class. Goodbye, everyone.